It's a joint work with two of my PhD students, so Louis Grognou and Maxence Noble here in École Polytechnique, and also a joint work with my colleague Marilo Gabriel. So it's our paper just have been accepted in ICML. So if you are in Vienna, don't hesitate to, in fact, say hello to Maxence or Louis, who will be there to discuss more about this work. All right. So first, I just want to emphasize a bit more about the application of our work and give some motivation. So maybe most of you, in fact, are motivated about this problem of sampling a distribution, but let's recall basic facts. So let's say the most basic example of application of sampling. So here I want to sample from a target density pi, and the prototypical example is for Bayesian inference, and we'll give you, let's say, a bit more details about it in a few slides. But in fact, I've learned a bit about, in fact, application of sampling more from a physical side. Because in fact Marilo comes from physics, and also other colleague of mine, for example Marie Michel, and in fact they explained me that in fact it's very important also, this problem is very important also in physics, in particular in statistical mechanics, in a theory which is called lattice QCD, and of course also in chemistry. So here in all this application we want to in fact it boils down to sampling a target distribution pi, supported here in this in my talk, supported in ARD. But in fact, in statistical mechanics, and for example, in fact,
sorry to interrupt you. Could you move the part of the interface of the Zoom interface somehow on the slide? Yeah, perfect.
It's better. Okay. Thank you. So. So I continue. So here in statistical mechanics, as I was saying, so one of the most simple example in statistical mechanics is called in fact the Ising model. And in Ising model, so here what you have in at n, you have in fact some what's called a spin, what are called spins, which are in fact in some lattices on R2 and on RD. And you discretize in fact your lattices, and you spin each spin, which corresponds to point on your lattices, can have only two orientation, which is minus or plus one. And you want in fact that you want to model what is called the magnetization of your material. And the magnetization of your material can be in fact characterized by in fact the average of the spin of your system. And in fact now in fact if you can look at in fact the average orientation of your system, and in fact in particular the distribution of the average orientation of your system, and depending on fact of the temperature of the system, you can have two behavior. If the temperature is high, it means that in fact the orientation of your spin is likely to be plus or minus one. In fact plus or minus one orientation are likely equals, and so here you expect that in fact the average orientation of your spin should be in fact be close to zero, which corresponds in fact to the black figures in the picture there. Whereas in fact if the temperature is high, you have the spins have the tendency in fact to have the same orientation, so either plus or minus one. In this case in fact you have some kind of what is called a phase transition, which means that in fact the average orientation is either concentrated around plus or minus one, and you have what is called in fact your material is called magnetized. And in fact the temperature where in fact you have a phase transition, meaning that you have exactly two modes is called the critical temperature, and is quite important to know, in fact, what is this critical temperature. And to this end, you need, in fact, to sample the distribution of your system to be able, in fact, to characterize the distribution of the average orientation of the spins. And that's why, in fact, also the sampling problem is very important in statistical mechanics. So here, okay, I also give you, in fact, some motivation, which is called from a theory which is called lattice QCD, which can be somehow can be thought as kind of a relaxation of the Ising model. And lastly, I also provide you an example in chemistry, where in fact you as you know, in fact, molecules are composed by atoms, but in fact the behavior, also the behavior of a molecule depend, in fact, on the orientation between the atoms. And here the position of the atom between each other. And here, okay, you can characterize, in fact, the position of atoms between each other in the example I provide you here, based on two angles, okay, on two different atoms. So here the angle here are described by the variable phi and psi on my picture. And here you can describe, so you can characterize, in fact, the behavior of your molecules depending on these two angles. And what you can also characterize your system based on an energy. And now, okay, you can sample from this energy to see, in fact, the constitution of different molecules. Okay, but here now, okay, the main challenge is, in fact, to explore all the landscape of your energy or of your target distribution to be able to characterize all the possible molecules that you can create depending on the angle between the two atoms. Okay, so here what to finish, okay, to conclude, what I would like to emphasize is that, okay, sampling, in fact, the distribution is very challenging also in physics, and it's very important. And in particular, in all the examples, in fact, I provide you here, okay, in fact, you start with the Ising model. In all these examples, in fact, you need, in fact, to sample from very multimodal distribution. And somehow, okay, that's the challenge that we try to tackle in this work. So I will not pretend that, okay, we can now, okay, sample all the multimodal distribution. It is still very complicated problems, but still, okay, we have, in fact, we try, in fact, to design design a sampling algorithm which try to tackle, let's say, we try, in fact, to sample multimodal distribution which are not, okay, too hard to sample. So I will give you, in fact, more detail in the numerical expression of our methodology, but that was, in fact, the main objective of our work. Okay. So now, okay, I can present you, in fact, also the motivation which come from Bayesian inference that maybe you are more familiar with. So here, in fact, Bayesian statistics, you have some observation Y. Based on this observation, you can put a statistical model which is specified by a likelihood, which in fact gives you, in fact, which provide you the probabilistic model of your observation given a parameter theta. And compare, okay, to frequency statistics. Here you suppose that theta is itself a random variable, and you choose a prior distribution on this parameter, and your favorite Bayes formula gives the posterior distribution, meaning the distribution of your parameter given your observation, and this posterior distribution is, in fact, has a density with respect to the prior distribution, which is proportional to the likelihood, meaning, okay, in my notation, L of y given theta. And here, okay, the main difficulty, which in fact also comes in physics, is that the target distribution in general, okay, you as a density, okay, but you have an expression for this density with respect to a reference measure. But this density is in general known up to medicative constants, and this, okay, comes with computational changes. And in fact, I will provide you some kind of reminder of what I've been suggesting in the past, okay, and maybe it will be a bit boring for some of you, but in fact I want to emphasize a bit about what has been suggested, in particular, in fact, what has been suggested in multimodal distribution. So first, okay, so here, okay, just to recap, so I want to try to provide an algorithm to sample, let's say, relatively easy multimodal distribution, and I suppose that, okay, I can have access to the log density up to an additive constant or the gradient of the log density. And here's all my density is my density pi, my target density is a density with respect to the Lebesgue measure known up to multiplicative constants. Oh. Okay. So now, okay, basic algorithms, the importance sampling. Okay, so but in fact it will give somehow provide me, in fact, somehow the common knowledge to expose you what is called the importance sampling and the sequential Monte Carlo. So here in importance sampling, I start from an instrumental distribution, which I denoted by rho here in red. Then, okay, in the importance sampling, you sample first some particle according to rho, and then, okay, you have first two stages where, in fact, you evaluate your instrumental distribution at the particles. So here it's in the second step. Now, in fact, you evaluate also the target density up to an additive constant or multiplicative constants particle based on these two computations. Now you compute the weight of each particle as the ratio of the targets at the particle over the instrumental distribution at the particle as well. Now, okay, you have the weights W of xi, but since in fact you know pi up to multiplicative constant, you need in fact to normalize the weights. And now, okay, for any test function f, okay, for which you want to evaluate an integral with respect to the target distribution, you can in fact approximate it by the sum, okay, of f of xi, where xi again.
But in this case, you will have a systematic bias if you do like this.
Yeah, of course. I was about to come to it, but yes, of course. So here, so you can approximate this integral as a sum, and in fact, you do not have the 1 over n, which is a typo. Sorry. So you can evaluate it. You can estimate as the sum of w of xi, f of xi, where the w xi are the self-normal weight, but as Sergio just said, in fact, since you do not know, in fact, in the pi up to make it constant, and you need, in fact, to use this self-normalized weight, you come up with bias estimator. But in fact, my point is not even that even if you are biased, okay, even if you are unbiased and if you know pi exactly, in fact, this importance sampling in general does not perform well in high dimension. All right. In general, okay, the variance of your estimator is especially even if you do not choose carefully your proposal, the variance of your estimator scales exponentially with the dimension, even in fact if you are log concave. Okay, so to circumvent this issue, okay, what has been in fact suggested is to use MCMC algorithm, and here is one of my favorites, which is, okay, the Langevin algorithm. So in the MCMC method, what you try in fact to design, you want to design a Markov chain, okay, for which pi is invariant or approximatively invariant. And so here, in fact, the Markov chain which I consider, xk plus 1 equals xk plus gamma gradient log of pi xk plus square root of 2 gamma zk. So here zk, in fact, corresponds to RID standard Gaussian, and gamma is the step size, because, in fact, this Markov chain corresponds to an Euler-Mariana discretization of the Langevin diffusion, for which, in fact, pi, you know that pi is invariant. Of course, using, in fact, a fixed step size here comes with some bias, but if you choose gamma small enough, the bias is relatively mild. So here, in fact, I present you two simulation of the Langevin algorithm. So on the left, you can see that the target is just a Gaussian. It's a Gaussian distribution for which, in fact, the Langevin perform very well. Okay, you can see that it's even the bias. You do not see really much the bias in the simulation at the end. Whereas, in fact, it does not. You can see that on the right, okay, the target distribution is a mixture of two Gaussian, for which the Langevin algorithm in this case performed quite poorly, because here, in fact, in red and green, it corresponds to two chains, okay, to two Langevin algorithm chains, started each in one of the modes. Okay, so here you can see that the Langevin algorithm is not capable, in fact, to exit the Bayesian of attraction of one of the modes. And it means that here, if you just look at, in fact, one chain, okay, somehow you are not really able, in fact, to escape one of the modes, and it means that, okay, the estimation that you will arrive based on the Langevin algorithm is very, very poor. Okay, and here when you can see it based on the empirical histogram associated with each of the chain compared to, in fact, in the black line, it really corresponds. In fact, it should correspond somehow to the true distribution. So you can see that, okay, the Langevin algorithm performs quite bad, and okay, it does not really work well for multimodal distribution. Okay. So now, in fact, for dealing with multimodal distribution, what I've been proposed is to, in fact, consider a path of distribution. So here, it's I consider a family of distribution is indexed by a continuous parameter t from 0 to large T, for large T, which in fact plays the role of what is called a temperature. And let's say in standard tempering scheme, in fact, Pt corresponds to what is called a tempered version of pi, which pretty much, okay, you can summarize pi t as a log concave combination of pi with an instrumental distribution rho for which you can sample from easily. Okay, so here pi t is proportional to the product of rho to the power 1 minus t over large T times pt over large T. Okay, so for small t equals 0, you end up with pi 0 equals rho. Okay, so here you start, in fact, so the first distribution corresponds to rho, for which, okay, you know how to sample from. Whereas, in fact, for pi t, okay, it corresponds to pi, which in fact the target distribution. And here now, in fact, you have somehow a path, okay, between pi 0 from rho, okay, the distribution that you can sample from, to pi. Okay. Now, in fact, so in general, okay, you do not try to sample all the pi t, okay, because you have, in fact, a continuum here, family of distribution. Here, you discretize 0 large T. You have, in fact, T1, T0 up to T large K. And, in fact, you try to consider now a fixed finite family of distribution, pi T0 up to pi Tk. And you try, in fact, to get approximate sample from pi Ti, okay, for I equals 0 to k. And you you go from, in fact, pi ti to pi ti plus 1 using standard MCMC methods. Okay. And in fact, okay, this type of algorithm have been a lot, in fact, analyzed and in fact enhanced by the MCMC community, because in fact it's really based on MCMC algorithm. So two of the main the sampling scheme based on tampering is either unidempotence sampling, which has been proposed by Neil, in fact, in 2001, which somehow consists in extending the target, the state space. Here you try, in fact, really to design an instrumental distribution on, in fact, an extended state space, for which, in fact, all the marginal, okay, of this extended instrumental distribution should, in fact, be quite good for PTI. Okay, and in fact, you can see, in fact, this unidempotence sampling is really a data augmentation approach, where in fact you try to design based on MCMC algorithm an extended instrumental distribution, which in fact should be quite efficient for importance sampling of an extended target, okay, for which in fact one of the marginal of this extended target is really the target pi that you want to sample from. So that's for unidempotence sampling. And here, in fact, but what is in fact what has been observed is that unidempotence sampling in fact can still have, in fact, large variance, and in fact to reduce the variance of unidempotence sampling, what has been suggested is sequential Monte Carlo on the right, and here in this sequential Monte Carlo algorithm, it consists somehow to try to use a raw Blackwellization procedure in the unidempotence sampling to reduce the variance of the overall procedure. Okay, but still, in fact, as I said, unidempotence sampling and also sequential Monte Carlo is somehow fundamentally based on the importance sampling algorithm, and okay, still, in fact, it's struggle in large dimension. Okay, so here it's we would like, in fact, somehow to address this problem, and that's okay. Try to have an algorithm which work for multimodal, let's say relatively easy multimodal distribution, but also in high dimension. Okay, and here again our approach is takes, in fact, it's a bit different than the tempered approach, but still, in fact, it's rely on a continuous family of distribution, pi t. But whereas, in fact, for the tempered approach, you use somehow low concave combination of pi with an instrumental distribution rho. Here, in fact, we take for pi t would be for any t the marginal of a stochastic process defined on 0 large t. Okay, and here, okay, what you would like, in fact, and I will show you, in fact, how to do so. In fact, you would like the stochastic process, okay, which will start from rho, which is easy to sample from, and which ends, okay, at pi. Okay, so that's, in fact, the building brick, the first brick, and the starting point of our approach is where it is. Okay, we still, in fact, as in the tempered approach, consider a family of distribution unlisted by the time. But here, okay, now we do not somehow we do not work directly on the density. Okay, here we work directly with a stochastic process, which is designed in such a way that, okay, it starts from the proposal distribution rho, and it should end to the target pi. Okay, so that's, in fact, really the first idea of our approach. So there are some relation to a diffusion model, and it's also connected with optimal transport via Schrödinger-Bresci approach. So I will not give you some detail about it, but okay, we can further discuss it after if you're interested. But okay, it's not very important. It's not at all important, in fact, to understand the algorithm. Okay, but in fact, not an important distribution, and that's somehow an interesting question you could ask is that okay, why in fact it could be more interesting to rely on stochastic process compared to the tempered approach, okay, in defining this family of distribution parity. And in fact, it appears to us that it is very interesting because in fact it's robust to what we call mode switching. So here is some simulation of what we call mode switching. So here in the dash graph is corresponding to the target distribution. So here you can see that you have unbalanced mode. So the mode on the left is more peaky than the mode on the right. Okay. And here, in fact, if you now consider, in fact, the evolution of the tempered distribution, okay, you can see that at the beginning, in fact, the tempered distribution puts more weights on the right, okay. So somehow it makes a mistake. It is wrong at the start in putting more mass, okay, on the wrong mode, okay. Whereas here, in fact, and somehow, okay, you have, okay, in the tempered approach, you can see that you have a transport of mass which is not very natural from the right to the left. Whereas, in fact, if you consider some continuous process, okay, you can, in fact, you can see that the family of distribution existed by the Tsar. Okay, in this case, if you consider stochastic process, you do not have this, let's say, strange transport of mass. But at the beginning, the distribution based on the stochastic process is capable to, in fact, distinguish, in fact, which mode is the most peak, and okay, you converge, okay, let's say, more smoothly to the target distribution. So that's.
Sorry, Alan, may I ask a question?
Yeah, of course.
Do you believe that it is related with the? Do you believe that it is related with generalization error, for example?
Sorry, I didn't. It was.
What I don't understand is, for example, you consider the continuous Time-Stein-Weinberg process, yeah, and you have you have perfectly smooth behavior in terms of mass transportation, and I don't understand why, if you consider its time discrete version, I don't understand why the tempering have so poor effects.
No, but here there is no discretization here, or very little. Because in fact, for the Stein-Weinberg process, you do not have even discretization. Because you can.
My question is that, okay, if you do very specific tempering, which you can interpret, for example.
No, because here the tempering. So here it's what you mean by specific tempering, because here it's really the continuous. You can see that it's really almost continuous here. It's almost a continuous tempering.
Okay.
So it's because I already have this question in here. It's what is crazy is that even it does not even comes from the choice of the discretization in the tempering. So here, in fact, the tempering is very small. In fact, so you can see that you cannot expect, in fact, this mode switching.
Sorry, I have a question. So
yeah.
The problem with tempering is that even after the two modes have separated, we have mass transfer between them.
Yes, exactly. Yeah.
Which can't be replicated by a local process.
Yes, exactly. So since you will use MCMC, in fact, to target to pass from one distribution to another, in fact, it means that okay, the MCMC algorithm will struggle at some point.
But stochastic processes don't have this problem.
Yes, exactly. Yeah.
Okay, thank you.
And the thing which I'm also a bit surprised is that it is not related with the tail behavior of the process. So, for example,
No, it's
you would say that, for example, with Ornstein-Uhlenbeck, you still have mod collapse, but then you take, I don't know, something with Cauchy-like tails, and then it becomes better. It would sound more expected to me, but it seems that it is not. It's not related.
No, it's really, in fact, how the mass is transport. It's really at the base. So we were quite surprised at the simulation, and we're quite pleased that, in fact, somehow it justifies the use of stochastic process compared to basic tampering. All right. So if there is no more question, I can move on a bit. Okay. So now, I think I present you somehow the basic idea of our method. So here I will, in fact, there is 2 questions in our method. Is in fact which stochastic process, in fact, to choose, and how to simulate this stochastic process, because that's somehow the 2 questions with that I will provide you some answer. And maybe, in fact, it will be a disappointment for some of you, but in fact I will not use at all any machine learning technique, no deep learning here. I will just rely on let's say basic sampling algorithm in this talk. And also, just for a notation which I will use a lot, so I will denote by calligraphic n y m sigma the density at y of the Gaussian density with mean m and covariance matrix sigma. So as I said, now, in fact, I want to define a stochastic process which address the constraint which I present you, meaning that it should start from a known distribution and end to the targets. And here is my stochastic process. So here I define yt for any t as alpha tx plus sigma wt, where x is sample from pi, sigma is positive variance, and wt is the d-dimensional standard point of motion. And here alpha is a function of the time, so we suppose that alpha is strictly increasing from 0 to t. So here, in fact, since x is supposed to be a sample from pi, so in fact, supposing that alpha is strictly increasing, in fact, it means that you gain more and more information. Alpha t brings more and more information about x as the time goes to increases. Alpha, we impose also that alpha 0 equals 0. Why is that? Because, in fact, it means that the starting distribution of y0 is simply the Dirac mass at 0. And then, in fact, it corresponds to one of the constraints which I want for the stochastic process I present you. So here, in fact, the distribution which will, in fact, I will be capable to sample from is simply the Dirac mass at 0. And then, I want, as I said, that the final distribution of alpha of yt, the stochastic process I just defined here, should be pi. And to this end, I suppose that alpha t divided by square root of t converge to infinity as t goes to large t. And here it will correspond to what is called the stochastic localization phenomenon. It means that, in fact, if I now divide alpha t divided by yt divided by alpha t, then as t goes to large t, this sequence of random variables converge to the sample x, and in fact, it means that it has the right distribution pi. And in fact, we can even, in fact, have easily bound to Wasserstein to distance between alpha t between yt divided by alpha t and x. So here, just for some notation, some vocabulary. So YT is called the denoising process, okay, or what we call, in fact, also the noising one. And T gives alpha T is called the denoising schedule. So the process, in fact, which I present you here does not come from nowhere. In fact, the case, okay, somehow the simplest case, which corresponds to alpha T equals T and sigma equals 1, have been suggested by Montanari recent paper. And in fact, it was one of our first, in fact, inspiration in the design of our algorithm. So here, okay, alpha T, I will call alpha, YT as the observation process. So we correspond to observing more and more, in fact, getting more and more information about your target density.
Sorry, Alan. For this particular process, I'm not sure that I quite understand why the last point is satisfied. Because you want that alpha of T divided by square root T goes to infinity as T goes to large T. But okay,
yes.
Then the limit will be just square root of large T for the examples that you present. Or you assume that you also start to increase large T somehow.
No, I will give you, in fact, some, because if you take alpha T, which in fact, if you take alpha T, which explodes as T goes to large T, where T is fixed, you're done. Yes. So here, in fact, in some application, so in some example, I would give you, in fact, alpha T, in fact, will explode as T goes to large T.
Because if alpha of T explodes, yeah, then I completely believe that it is fine.
Yeah. So I will give you, in fact, some example in the next slides for which it holds. Then okay, so pi T is YT is my observation process. In fact, the family of distribution pi T, which I consider here, is not the distribution YT. In fact, it will be, in fact, as I think you already guessed, is pi T is the marginal distribution of YT divided by alpha T. Okay, and here I define, okay, my sequence of my family of distribution fixed by the time. Okay. So somehow, okay, and I will give you a bit of a teaser. So now, okay, I have defined, I fixed my stochastic process. So in fact, we have in mind also other stochastic process, but okay, that's the first one. In fact, it's one of the most the simplest one. But okay, in fact, I will come back to it in a minute. But you can see that, in fact, in the simulation of YT, it's quite challenging because, in fact, when you look at the definition, in fact, from this distribution, sampling from YT should require somehow a sample from pi. You can see that, okay, the reasoning is a bit circular first, but in fact, okay, I will show you, I will give you, in fact, some further result on the stochastic process YT, from which, in fact, we will be able to sample YT without, in fact, sampling directly pi. Okay. So as I said, okay, here, in fact, the reasoning seems a priori a bit circular because, okay, first, from the definition of YT, it seems that we need a sample from pi. But in fact, we can rely on what is called the Markovian projection of YT. Here, in fact, what you can show is that, in fact, YT is a solution of the following stochastic differential equation. So dyt equals alpha dot tut of YT dt plus sigma dwt, starting at y0 equals 0, where, in fact, the drift is non-homogeneous in time. Ut of y is equal to the conditional expectation of x given YT equals small y. Okay, so here you can see UT as kind of a denoiser, all right, of your observation of the sample x from the sample x given the observation process YT. Okay, so that's, in fact, somehow a basic a basic result in probability. And now, okay, based on this characterization for the stochastic process YT, you can in fact try to sample YT if you would have in fact access to the denoiser UT. Okay, but even in fact if you would have a perfect knowledge and access to the denoiser UT, okay, in fact integrating this SD explicitly, in fact, is not possible, and you need to rely on a discretization. Okay, and here, in fact, we rely on a Maruyama discretization of this stochastic differential equation. So here we just define the sequence YK, okay, which corresponds to the discretization of the process item TK, okay, where TK is a given discretization schedule on the interval 0t, where YK plus 1 is equal to YK plus WKU TK YK plus sigma square root of delta K ZK plus 1, while delta K corresponds to the increment between TK plus 1 and TK, and WK corresponds to the difference between alpha TK plus 1 minus alpha TK. Okay. So here, in fact, the first somehow sanity check that we explore is that okay, even okay in some situation, okay, you can have access in some very simple situation, you can have access to the drifts here for some target density. And what the first sanity check is that okay, if you can have access to the real drift UT, is in fact the Euler-Maruyama discretization of the SD associated with YT gives you, let's say, reliable sample from the target distribution. And so here we perform some empirical evidence here for the case where the target distribution is a mixture of two Gaussian again, for which in fact you can compute explicitly.
Here you assume that you know UT. Yeah.
Exactly. Yeah. And for this particular example, in fact, for a mixture of two Gaussian, you can have access explicitly to the drift. And here we really wanted to first check that in fact, if you use a discretization, a simple discretization of the SD with YT, that you come up in fact with good sample from the target. And you can see that in fact here we take alpha t, okay, the simple choice alpha t equals t and large t large enough, and also a case where in fact the horizon t is set to 1 and alpha t in fact explodes as t tends to 1. And you can see that in both cases we get in fact a quite good approximation of the target in these two cases. Okay, so now in fact that we are quite confident that okay, using discretization is not really an issue. We can come up with the problem of estimating the drift UT. So I will skip in fact okay some consideration of how to choose carefully the discretization. Here now in fact I would like to see how to estimate the drift UT. Somehow okay, just I wanted to cite and make some discussion about what I've been discussed before, and in fact make some connection maybe with diffusion score with diffusion model. Now, in fact, okay, you can try in fact to estimate this denoiser by in fact you can try to estimate the denoiser by variational approach, okay, and try to estimate directly this drift by minimizing by minimizing the Kullback-Leibler between the true in fact, between a family of diffusion with a drift parameterized by f theta here in my example, with in fact the drifts with the distribution associated with a truth process yt, and in this case, okay, you come up as in diffusion model with a mean square problem, but in this problem, okay, when you need in fact to sample from x, it means okay, you need in fact the functional in fact is defined as in fact an expectation over x, and if you would like in fact to minimize this functional in practice, you will need in fact to sample from pi. Okay, so here you cannot do this because
here it looks a bit circular in the sense that you tried to avoid sampling from P from the very beginning.
Yes,
you ended up with something that still requires sampling from P.
Exactly. So you cannot do it. That's exactly my point. You cannot do it.
Then okay.
So here, in fact, another approach. Okay, so in this case, in fact, it just consists in considering not the the forward Kullback-Leibler divergence, but the backward. So here, in fact, you take a family of diffusion, okay, which in fact, a family of diffusion corresponds to diffusion with a parametric drift, okay, and if you denote by p theta the distribution of the corresponding diffusion, and you want to minimize the Kullback-Leibler divergence between the path measure of yt and this p theta. Okay, it can be done, okay, using some tricks, but you need, okay, now in general, okay, you need to rely on a neural network to learn, in fact, this drift. And here we do not, in fact, want to use this, let's say, very computationally heavy tools. Here we just need, as I said, to use Monte Carlo methods. In this case, and do not rely on we do not want to use such heavy computational tools. Okay, so here we really want to take a non-parametric approach and use at the end only Monte Carlo algorithm. And in fact, just to also give you some discussion. So there have been also some paper which have been appeared in iClear this year, which takes the same approach in Sarmi et al. In Wang and co-author, where in fact, okay, so Sarmi and co-author take, let's say, a perpendicular approach, but our approach looks like more Wang et al. In particular, in fact, the first part of our approach is exactly the same, but the second part is not the same. Okay. So now, okay, I want to estimate, in fact, so ideally, in fact, I just recall you what will be the ideal algorithm. Here, in fact, in the ideal algorithm, okay, you just define your sequence of discretion yk plus 1. Yk plus 1 equals yk plus wk plus, okay, your quotient increments, where uk is equal to utk yk, where in fact, now, in fact, I can give, let's say, a bit more explicit expression of uty. So uty is equals to, in fact, the mean of the posterior distribution of the sample x given yt. Okay. So here, what does it mean? It means that, okay, here so here the distribution of x given yt. Okay, so here if you just use Bayes formula, okay, since yt is equal to alpha t x plus sigma wt, you know exactly, in fact, the distribution of x given yt, and it has a density q, which I denoted here by qt of x given y, which is proportional by Bayes formula to the product of pi of x, the distribution of y given x, which is a Gaussian density with mean alpha tx and variance sigma square t as the identity matrix. So here is, in fact, some kind of somehow an explicit expression of uty, And now, in fact, you can come up with one natural idea is simply, in fact, to use a Monte Carlo strategy to come up with approximates, in fact, some kind of estimator for UK. Okay. So here it is. So here, in fact, since in fact Qt, you know, in fact, Qt of x given y. Okay, you know, in fact, the expression of this density, of this conditional density up to a normalizing constants. Okay, but here you know this. Since you have access to pi up to normalizing constant or gradient of log pi, you can also try to estimate to get approximate sample of Qt of x given y using MCMC algorithm, and that's what we suggest here.
Recording stopped. Recording in progress.
And that's what we suggest here is, in fact, to at each iteration, so given yk, okay, we get approximate sample of Qt x given yk, okay, using MCMC algorithm. In particular, okay, in our experiments we use Mala, and based now on this sample, you can compute the corresponding average of this sample. It gives you, in fact, the empirical mean associated with your MCMC algorithm, and you plug in, okay, and the Monte Carlo estimated for UK, and you replace, in fact, now UK with this this Monte Carlo estimator, and you get somehow a practical way to implement the discretization of yk.
And you performed sampling for different t's independently? Or?
Yes, exactly.
Because it seems that, for example, when t increases, the problem becomes simpler and simpler because the distribution becomes log concave with very strong, with very large constant of strong convexity. It becomes almost Gaussian. Yeah.
Yes, exactly. So here, in fact, we that's in fact the main one of the main observation that we made is that, in fact, the question which in fact related to your remark and comments, Saryosha, is that here, in fact, the basic question that you could ask is that, in fact, when you look at the expression for Qt, you can see that so Qt is a product of pi with somehow convolution, kind of convolution between pi and Gaussian distribution. But still, in fact, you could wonder, okay, when, in fact, sampling from Qt is easier than sampling from the initial target distribution. And in fact, you can exactly characterize how it is the case. So, in fact, we take very simple assumption. Okay, we can, of course, and we think we know how to do it to extend the assumption which I present you. But here, in fact, I take very simple assumption that, in fact, if x is a sample from pi, in fact, x can be decomposed in the sum of two variables, so u plus n, where u is a bounded random variables and n is a Gaussian random variable. So this assumption is satisfied for mixture of two Gaussian, or in fact mixture of multiple Gaussian. And here you start with this assumption, and we try to look at, in fact, if we can, in fact, characterize time for which sampling from Qt is easier than sampling from pi. So I will skip, in fact, some general remark, which is not very important. The true, in fact, result is as follows. So here, in fact, we can completely characterize, okay, we can, in fact, based on this assumption, we can, in fact, exhibit time tq, okay, between 0 large t, such that, okay, after time tq, okay, Qt is strongly log concave. Okay, so what, in fact, is important for sampling is that, in fact, what is known is that if a target distribution is strongly log concave, Mala or the Langevin algorithm perform quite well. Okay, you can use really, in fact, one of these algorithms to sample from the target distribution. So here, what in fact this result said that, as in fact Sergio had the intuition that okay, after long enough time, in fact, you can use in fact, let's say, Langevin or the Mal algorithm to get approximate sample from Qt, and okay, you do not need in fact many samples because you already know that in fact the algorithm perform well. Okay, so that's for the first result, but still in fact, okay, there is an issue because okay, how to do in fact for t smaller than tq, because here you really need in fact to sample all the process. All right, so that's the second question that we will address in the next slide. But okay, just to illustrate this result, okay, you can see on this video that okay, here's the behavior, okay, the evolution of the conditional distribution Qt with the time. You can really see that okay, at the beginning you are really in fact you look like very much with as the multimodal target, which is again mixture of two Gaussian, and you converge somehow with more and more concentrated concave distribution. Oh. So now, in fact, okay, you as I said, you at the same time, okay, you need in fact to sample all the process. Okay, you would like in fact to really sample all the YT, and here somehow the simple solution with that will come up is that okay, we will not in fact sample our process from 0 to T0 for T0, which is strictly greater than TQ. Or we will not in fact simulate over 0 up to some time. So here in fact we'll start our process at T0, okay, and then okay, follow the diffusion. And now the main question is that okay, how to in fact initialize my process, how to sample from YT0, and for T0, okay, which is ideally strictly greater than TQ, because okay, I know in fact I know how to have, let's say, good estimator of my drift only for time which is strictly greater than TQ, because okay, I know that in this case I can use efficient MCMC algorithm to get approximate sample from Qt. So that's now the main question that I want to address. Okay, can we have somehow an efficient, an approximate sample of YT0? Okay, so just a bit of a notation to explain a bit more about the algorithm that will come up. So here, as I said, okay, the drifts that appear in the diffusion associated with YT is the conditional mean associated with the posterior distribution of each given YT. And now, okay, here what we are interested in mainly is in sampling from YT0. And here, in fact, for any t, I denote by pt of y the marginal distribution of yt, okay, at time t. So it corresponds simply of in fact, the integral of the product of the posterior distribution, okay, but you integrate with respect to the sample x. And in fact, what's in the crucial observation that we made for getting an approximate sample from YT0 is that in fact you have somehow a strong relation between the drift, okay, the conditional mean associated with Qt, and the score associated with the marginal distribution Pt. In fact, the 3D formula gives you that in fact the drift Ut of y is okay up to simple transformation is okay simple transformation of the score of Pt. Okay, so here Ut of y is equal to y divided by alpha t plus sigma square t divided by alpha t gradient log of Pt of y. So again, in fact, if you would have access to Ut, right, you would have in fact also access to the score of the marginal distribution of Yt, okay, and okay, you could use the Langevin algorithm or Mala. In fact, here you can only use the Langevin algorithm to get approximate sample from YT. Okay, because here you have somehow an expression for the score of PT, but you cannot use Mala here because you do not have access directly to the density parity because it's as a form of an integral. So here the idea is in this way. So, but I will just keep maybe directly the algorithm, and I will comment it maybe later. I want to give you the algorithm now. So in fact, now the main idea now to get an approximate sample from PT0 is to use what we call Langevin within Langevin initialization. So here we initialize in fact Y0. Okay. Now, based on this initialization, we perform Mala to get approximate sample, to get an estimation, in fact, to get approximate sample of the condition distribution of X given yn minus 1, where yn minus 1 is the current estimate of an approximate sample of YT0, right? Now, based on this Mala step, I can estimate the drifts, based on this sample from Mala. It gives me, in fact, what I denote by un minus 1, which gives me, in fact, an approximation of the drifts, of the condition expectation associated with the condition distribution of Qt0 of X given yn minus 1. Now I can use, in fact, 2D formula to get an approximation of an estimator of the gradient of my score at T0. And I can use one step, of the Langevin algorithm to update yn as yn equals yn minus 1 plus lambda, the estimation of my score of gradient log PT0 plus a Gaussian increment. And where lambda here is the step size, that is used for the Langevin step. Then, I can do it, large n times, and hopefully, in fact, I could have analyzed the overall algorithm.
If you do like this, why you don't simply take very large T0, for example, very close to the end of the interval? Like, where is some trade-off between, I don't know, intuitively it should be some trade-off between the choice of T0 and, I don't know, number of Langevin steps performed or complexity of Mala sampler or something like this.
That's a very good point again. So thank you very much. So here, in fact, I can come back to my last slide. So here, in fact, the main question that you can ask is, sorry, I'm not used to, okay. So here, in fact, what's the question that you may ask is that now, in fact, PT is the marginal of YT, but you could ask, in fact, the same question as for the estimation of the drift of sampling from Qt of X given Y, in which situation sampling from YT is easier than sampling from the target. In this case, in fact, the log concavity property of PT is the inverse from as compared to Qt. So here, in fact, PT is strongly log concave only if T is small enough. In this case, under the same assumption that we consider. So here, that's exactly the trade-offs that you mentioned here. That's in fact for T0.
For reverse process, yes, that's the case.
Yes. So for T0, in fact, somehow it's exactly what you thought. It means that for T0, in fact, what you expect, you need to for T0 to be, in fact, between what you expect. That's somehow a very strong assumption we make, but in fact, I will comment a bit more about it. But if now, in fact, TQ, the interval TQ and TP, where TP is the maximum time for which PT is strongly log concave, is non-empty. You could choose, in fact, T0 between TQ and TP. And in this case, you can, in fact, sampling from PT0 is relatively easy using the Langevin algorithm. And in fact, the estimation of Qt0 can be done also efficiently. Okay, so that's you have exactly a trade-off in the choice of T0, because in fact PT is easily sampleable only for small t. Okay. So as I said, okay, so you in the illustration I gave you, in fact, I suppose that TQ and TP, in fact, the interval is non-empty, so it's rarely the case, in fact, in the application. But the main idea, okay, which I want to illustrate on a short video, is that in fact what you try to look at is somehow a T0 for which, in fact, sampling from QT and sampling from PT is, let's say, relatively not that complicated. So here you really try to spot a good time for which, okay, the both distribution, okay, are not too multimodal, and that's exactly here. For example, in this numerical illustration, you can see that if you choose, in fact, this T0 in green here, you can see the two distribution on the right, okay, are relatively easy to sample from, okay, compared to the original one for PT0 or the initial one for QT and the final one for PT. Okay, so I think time is almost over. So okay, the overall complexity of algorithm, okay, I can send you my slides. Okay, it's what you can adapt. Okay, it's not that it can be quite costly, but all in fact sampling methods which are based on particle. And here, okay, I will not go beyond, in fact, the concurrent work. I discussed a bit already. I want really to illustrate our method on some experiments. So here, in fact, I will consider an experiment, quite simple experiment on a Gaussian mixture for increasing dimensions. That's what somehow is one of the purpose of our algorithm. So here we go from dimension 8 to dimension 64, and we compare our algorithm with different alpha. So here, sleep standard corresponds to alpha t equals t, okay, the simplest one, whereas in fact geom 1,1 and geom 2,1 corresponds to alpha which explodes, and for which, okay, the time horizon is equals to 1, as I already illustrated you in the previous slides. And here you can see that here, so we evaluate the quality of the algorithm on two metrics. So the first one is what is called the Slash-Wasserstein distance, okay, which is a particular distance on the probability measures. And on the other metrics, we in fact try to estimate the weight of the mode in the mixture. And particularly, in fact, we are in fact we report here the estimation, the ratio, okay, between, in fact, the true weight and the estimated weight. So you can see on for both these metrics, our algorithm performed quite well compared to this competitor. So especially, in fact, regarding the mode weights, in fact, so yeah, we are quite. So you can see that for in the estimation of the weights, IES and SMC perform quite poorly compared to the other algorithm, and our algorithm perform better than the, let's say, closer competitor, which is ROT. And RDMC, which is in fact the true work I already mentioned, which takes a non-parametric approach as our work. All right, so here is for somehow the synthetic data and synthetic experiments, and here in fact we consider that's a more challenging problem, which is a phi-4 model, which in fact is part of the lattice QCD theory, which I just mentioned at the beginning of my talk. So in this case, okay, in this lattice QCD theory, what you would like, okay, ideally to have to sample from some pass, the distribution of some pass, okay, on some grid, not on some grid, but on R2. But yeah, okay, since in fact you cannot directly sample from this this distribution is defined on too complicated state space. Here you discretize in fact your state space and you take just some grid. And here, okay, you can the distribution that you ended up in fact is plot here, is represented here. So you can see that the distribution is composed of two modes, okay, which corresponds to, in fact, the red curve and the blue curve, okay. And here, in fact, you have some the distribution is really concentrated on these two paths on this picture. And now, in fact, so you have, in fact, two modes which are known, so that you can compute these two modes. But what is not completely clear in this model, in fact, is to estimate the relative weights of these two modes. And to this end, okay, physicists has come up with some approximation. So we can use either a first Laplace approximation of a second one, for which, okay, you can have so you come up with approximation of the relative weights of the two modes, and we try in fact to compare this approximation with the result of our algorithm. And here is our results. You can see that in fact our algorithm performed quite well, okay, especially in fact slips using in fact alpha, which explodes which explodes for a finite time horizon. But even in fact let's say the more standard slips algorithm perform quite well. So it ends my talk, and thank you very much again for your invitation. If you have any question, that's
Yes, I have a question. Thank you for your talk. Yes. I wanted to ask the stochastic process that you define with alpha depending on t, it explodes, right? So how can we do numerical simulation of this process if and approximation if it explodes? I don't understand.
So yeah, in fact, okay, you do not in fact discretize up to the time horizon. Okay, you take somehow a margin, of course, and you take in fact step size which are smaller and smaller close to the time horizon, of course.
So we do not go to the time horizon completely.
No. You stop before, of course. Yeah.
Okay. Thank you.
Thank you. Are there more questions?
Okay, I have plenty of questions, but I think that we can continue. We can continue later. So that's. But you have a very nice talk. So I'm very pleased that you find time to come to our seminar.
No, thank you very much. It was my pleasure.
Thank you. So, no more questions? If it's not the case, then thank you very much, Alain. Thank you.
Thank you. Bye.
Bye-bye.